Hi everyone, I'm Jose Algarin, Program Specialist for the Climate Variability and Predictability Program, CVP, at NOAA's Climate Program Office. Thank you for joining us for the 8th and final session of the webinar series called Decadal Climate Variability and Predictability Studies. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinar is being recorded and will be available at the CVP website under the Webinars tab. If you missed any of the prior webinars, I encourage you to view them from our website. CVP supports research that enhances our process-level understanding of the climate system through observation, modeling, analysis, and field studies. This webinar series covers the 10 projects funded by CVP on the topic of decadal climate variability and predictability studies, all of which started in September 2020. The call for these studies was CVP's contribution to the national and international research interest in this topic. The main goal of these modeling studies is to identify the state, mechanisms, and sources of climate predictability on the interannual to decadal timescale. This research will lead to future improvements in skillful decadal prediction systems for climate, ocean, and atmosphere. In this series of webinars, researchers will share the latest results from these projects and will allow them to discuss the importance of their work, outcomes, and lessons learned with a broader scientific community. We hope that you will enjoy today's talks and ask plenty of questions. Speaking of questions, if you have one for our presenters, please use the raise your hand feature, which you can find at the control panel for GoToWebinar. We're going to do something different today. Since we have 3 speakers today, we will hold all questions until the very end. So if you have a question for our first presenter, please write it down, and we're going to ask them at the end of the all 3 presentations. I will unmute those who have raised their hands so that they can ask the questions using the audio. You'll also need to unmute yourself after I do so. If you have other problems, I will ask you to type your questions in the questions box, which can also be found on the control panel. Now let's get to the presentations. Our first speaker today is Dr. Ke Chen. He is an associate scientist in the Physical Oceanography Department at Woods Hole Oceanographic Institution, Hui. His research interests include coastal ocean dynamics, self-ocean exchange, and the interactions of the coastal ocean with the larger scale climate system. Dr. Chen uses a wide variety of numerical modeling in his research, but also uses observations whenever possible to achieve integrated studies. Some of his recent works include the interaction of the Gulf Stream warm core rings with the shelf circulation, mechanisms of marine heat waves, physical biological interactions in the mesoscale eddies, and drivers of the shelf circulation in the Northwest Atlantic. Dr. Chen, thank you so much for joining us at this time, and I will turn over the controls to you. Now you're able to present.
Okay. So can you see the screen now?
Yes.
Okay, great. All right, so thanks everyone for joining this webinar, and thanks Jose for the introduction and also the invitation. So today I'd like to briefly talk about some of the products coming from our CVP project, the title of which is shown here, investigating the connection between AMOC and the Northwest Atlantic coastal sea level, connecting the dots across the shelf break. So this research project requires a good understanding of open ocean processes, including AMOC and its different branches. Coastal ocean processes, especially those can lead to sea level change, as well as the mechanisms that can connect the open ocean and the coastal ocean. My co-PIs are Jiayan Yang and Jian Zhao. Both will be speaking shortly, but in my presentation, I'd like to focus on one type of process that can link the open ocean and the coastal ocean. And that brings me to the title of my talk, which is Mesoscale and Submesoscale Shelf Break Exchange Drives a Subsurface Marine Heat Wave in the Northwest Atlantic Coastal Ocean. So this work was done in collaboration with my long-term collaborator, Glenn Grogwith and Jiayan Yang, both at Woods Hole. Now first, just to get everyone on the same page, I'd like to briefly talk about the oceanographic setting. So here you are looking at a monthly mean sea surface temperature for the region of interest, which is Northwest Atlantic Coastal Ocean. So the mean circulation in this region includes an equatorward shelf current flowing from north to the south, and offshore Gulf Stream is pushing poleward. And between the Gulf Stream and the shelf is the so-called sloop sea, where Gulf Stream meanders and warm core winds can have a big impact on the oceanographic environment. So because of the high latitude influence, the shelf water is generally cold and fresh, in contrast to warm and salty slope water. And separating the shelf of the slope water is the front, which is dynamically trapped at the shelf break, roughly around 200-meter isobath. And this is the shelf break front. There's also a frontal jet associated with the front. So this region has been experiencing long-term spatially coherent warming. In the top panel, you are looking at sea surface temperature anomalies averaged anywhere between Labrador Shelf and the Cape Hatteras across 4 different SST products. And you can clearly identify a long-term warming trend. And the warming rate is roughly 0.4 degree per decade. And that number is actually getting larger in recent years. That's the notion of accelerated warming. And on top of this long-term warming, you do see large interannual variability with extreme events, that is marine heat waves, which are defined as ocean extremes with a large temperature anomaly. And the most prominent marine heat wave in this region is the one in 2012, which you can see here, set the record high temperature in the past 100 plus years. And here's a map showing the spatial distribution of the sea surface temperature anomaly in the first half of that year. And you see large temperature anomalies exceeding 4 degrees, and that's larger than 3 standard deviations. So quite anomalous event. And as you can imagine, marine heat waves, such as the one in 2012, can have widespread impact on the physical and biological environment. So that's why we need to have a better understanding of the driving mechanisms, which is a foundation for reliable deterministic prediction. Now in 2017, another marine heat wave happened in this region, but what's different about this one, this is a subsurface advective event. So here you are looking at 2 histograms, one for depth averaged temperature on the left, and then to the right, you are looking at depth averaged salinity histogram. So 2017 conditions are marked in red. So in comparison to all the historical values in this region, this is, by the way, to the south of a New England shelf. So the 2017 conditions were really anomalous. So temperature anomaly is above 4 degrees, and that's exceeding 98th percentile. And salinity is larger than 1 PSU, exceeding 97th percentile. So truly anomalous event. And what's more interesting is that this is a so-called a compound event, meaning we have a large anomaly in both temperature and salinity. And this compound nature actually is a strong indication this event was likely driven by oceanic processes, because atmospheric forcing shouldn't be able to produce such a large anomaly in salinity. And we have some evidence to support this idea. So here you are looking at the 6 AVHRR SST images from November of 2016 through February of 2017. So quite clearly, you can identify a few warm core rings in close proximity to the shelf. And we know that warm core rings can play a big role in terms of changing the shelf conditions. So it's reasonable to think that warm core rings were driving the water mass anomalies that I showed you earlier. And that's what we hypothesized. So what we thought happened was warm core rings, specifically to the south of the New England shelf, was able to bring warm and salty water onto the shelf and to generate that subsurface event. And then that water mass anomaly sort of rise on the mean along shelf flow to the south and finally exits the shelf in April of 2017. So again, this is a very reasonable hypothesis that warm core rings were driving those water mass anomalies. But still, there are a few questions to be answered. Number one, whether or not warm core rings are indeed important. So we were not able to do a thorough proof using existing data, simply because observations were not enough. And number two, what is the exact working mechanism? So we know that the shelf break, which in this map is the thick black contour here, is an effective barrier dynamically in terms of inhibiting water mass exchanges between the coastal ocean and the open ocean. So for the water mass anomaly to propagate across isobath, some higher order dynamics must be present. And number three, what about other factors like atmospheric forcing during this event? So answering those questions is the central motivation of this study. And to do so, I use realistic numerical modeling. So just quickly, this model is based on regional ocean modeling system ROMS, and horizontal resolution is 1 kilometer. And as I will discuss later, this high resolution is essential to resolve some of the important bathymetric features. I don't want to go through all the technical details here, but instead I would just tell you this model has very good scale in terms of reproducing the temperature and the salinity field, and also their variability over time. Overall RMS error for temperature is 0.8 roughly, and that's a good number for a model without any data simulation. And for salinity, RMS error is roughly 0.4, again, indicating a very good model scale. Before I show you the results, I'd like to give you a quick preview what happened. So the dynamic process about this cross-shelf connection works in 2 steps. The first step is the preconditioning by cyclonic eddies. So what the cyclonic eddies do is 2 things. One is to change along-shell pressure gradient, and number 2, inducing frontogenesis. Both processes can bring warm and salty slope water onto the outer shelf. The second step is persistent upwelling wind drives a bottom intensifying intrusion from the outer shelf all the way to inner shelf. And the intrusion about this event, the unique thing about this is it is localized along a bathymetric depression. Now first, looking at the first step, the preconditioning of the cyclone eddies. So here you are looking at a snapshot from the model. So in the top 2 panels here, you are looking at the surface temperature and the surface salinity, along with the ocean currents in black vectors and wind vectors in white. And in the lower 2 panels, you are looking at the temperature and the salinity field at 50 meter. Now, the first thing I'd like to point out is the model produced a sea surface temperature field that compares well with AVHRR SST on the same day. For example, you see the warm core ring to the east and the extension of warm water to the west. The general spatial pattern is captured well by the model. But what the satellite SST does not capture, but the model clearly does, is the presence of a smaller scale cyclonic eddies, which are marked in blue crosses here. It might be easier to see from the subsurface map. Now, the presence of cyclonic eddies in this region or in the periphery of the warm core rings has been long identified. This goes back to the warm core ring program in this region almost 40 years ago. But the eddies, the cyclonic eddies, are rarely discussed in the literature in terms of their roles of cross-shelf exchange and also other dynamic processes. But now this model clearly captures those smaller scale eddies, and we should be looking into the processes associated with them. One process that I like to mention here is frontogenesis. Now here's a schematic showing you the basic idea of frontogenesis. So basically, when there's a cyclonic eddy impinging upon the shelf break, on the onshore flank of the eddy, the flow goes equatorward, or going out of the page, if you will. And the existing shelf break jet is also equatorward. So the flow direction is the same. So then you can imagine there will be flow confluence, and the shelf break jet will be accelerated. In the meantime, the impingement of the cyclonic eddy will sharpen the existing shelf break front. So this is the basic working of frontogenesis. And according to semi-geostrophic theory, the acceleration of the frontal jet in this direction has to be compensated by cross-frontal secondary circulation in the vertical plane. And if you try to understand the secondary circulation using PV conservation, you will get a flow pattern like this. So downwelling at the denser side of the front and upwelling at the lighter side of the front. And then the secondary circulation sail goes clockwise. So on the left, you are looking at two snapshots from the model from which you can see some evidence of frontogenesis. So in both examples, you see cyclone eddies interacting with the shelf flow. And at the location where they interact, the second term is the horizontal buoyancy term. You see large frontal structure here. And the third term is showing you the frontal tendency, which is telling you whether or not the front is getting stronger or weaker. And you do see along the front, many places, the front is getting stronger. So to give you a better idea of the frontogenesis process, I'm going to show you a cross-section here to show you the frontal diagnostic terms. So the first panel here is the along shelf velocity, from which you really see the surface intensified shelf brick jet going equatorward. And the salinity field and also the frontal sharpness term gives you an idea of the location of the front. Relative vorticity scaled by F in this panel, this gives you the Rossby number, is order 1. Actually, this is already much larger than 1. So we know the flow is highly nonlinear, and this is already in some mesoscale regime. Both frontal tendency and the secondary circulation pattern are consistent with the theoretical understanding of the frontogenesis process. So again, downwelling at the denser side, upwelling at the lighter side. There's onshore flow at the subsurface. So I should mention the time scale of frontogenesis is short, usually on the order of days, and also spatially it is intermittent, which probably you have seen already from the last slide. But still, this secondary circulation pattern is effective in bringing offshore warm and salty water onto the outer shelf to change the temperature and the salinity field there. So that's why I like to call it a preconditioning process. Now looking at the second step, I'm showing you the bottom salinity field in color, along with ocean currents along the sloping bottom in white vectors. And the wind stress curve, the wind stress vector is showing in cyan. This is for the last 6 days of January 2017. Again, this is a realistic simulation. So you see the wind is upwelling favorable, blowing from west to east. So if you think, a traditional two-dimensional upwelling wind-driven model, you would expect the onshore migration of the bottom high salinity water. And that's what you see here. So for example, on day 1, if you look at the leading edge of the high salinity water, is roughly along the 100-meter isobath, which by the way is a thicker contour. And after 6 days, that high salinity leading edge is already past 100-meter isobath, so it's moved further onshore. So that's consistent with the 2D model. But what's more interesting here is this localized intrusion along this topographic depression here. The horizontal scale is roughly 30 kilometers, and this intrusion extends from the shell break to almost 50-meter isobath, so over a very large spatial distance there. And if we take a cross section cutting through this the core of the intrusion, we can see this was indeed a bottom intensified intrusion. The vertical scale is roughly 10 meters, and within 5-6 days, the high salinity, high temperature core moves from the edge of the shelf to, again, almost 50-meter isobath. And that's just in a distance larger than 100 kilometers. And if you do back of the envelope calculation, you will get an advection speed of 0.2 meters per second. So which I should point out, this is a remarkable number because this is the same magnitude as the equatorward shelf break jet. So very remarkable and rapid propagation of the water mass anomaly. Now the question is, what is driving this bottom intrusion? So here I'm showing you the pressure gradient field in color, along with vectors telling you the direction of the pressure gradient force. I'd like to draw your attention to this, this localized pressure gradient setup along this topographic depression. So for example, looking at panel B, you have an elevated pressure gradient force here, and the direction is pointing to northwest, this direction. And the major momentum balance during these 6 days is between Coriolis and pressure gradient. So the resulting onshore flow should be pointing to northeast if you think about, geostrophic perspective. And that's what we see here on the same day. Onshore flow pointing to northeast. And also in the last 2 days, because of the relaxation of the upwelling wind, this localized pressure gradient setup gradually disappears. Again, that's consistent with the disappearance of the onshore flow. So the message here is relatively clear. That is, the localized bottom intrusion during this time period is driven by the same spatial setup of the pressure gradient field. Now you may still wonder, what's setting up this pressure gradient field? And I'm going to use this simple schematic to briefly explain. So you are looking at an idealized shelf topography. It's no longer a straight coastline. And on the right, you are looking at the southern New England shelf here. And to the left, you are looking at the New York Bight area here. And the wind was blowing from west to east. So on the southern New England shelf, or to the right, you can think of that classic two-dimensional Ackermann model, right? Surface Ackermann transport across the shelf. So we have a higher barotropic sea level setup offshore and lower sea level along the coast. And then on the western shelf, because the wind direction and the shelf orientation do not align, there will be Ackermann transport in both cross shelf and along shelf direction. So if you think of the bulk effect of the Ackermann transport at the intersection of the western and the eastern shelf, you will have a elevated barotropic sea level setup. And that is in contrast to a lower barotropic sea level setup on the western shelf. And then you're going to have an enhanced pressure gradient field at the intersection. And in addition, this topographic depression here is going to help facilitate, the pressure gradient setup to drive onshore intrusion of a warm and salty slope water onto the shelf. I think I'm going to stop here. The take-home message really is the combination of cyclonic eddies and the upwelling wind can be an effective mechanism to connect the open ocean processes to the coastal ocean. And consideration of a three-dimension features such as along shelf bathymetry is very important if we want to have a better understanding of shelf ocean exchange in general, or the origination of extreme events such as marine heat waves on the shelf. So for those of you who are interested, here are the 2 papers. You can find more information about this topic. Alrighty.
All right, thank you so much, Dr. Chen, for that great presentation. Right now, as I said in the beginning, we're gonna move to the second presentation, and then all questions will be held until the very end. So our next presenter is Dr. Yang. He is a senior scientist in the Physical Oceanography Department at the Woods Hole Oceanographic Institution. His main research interests are dynamical processes that govern ocean circulations and their variability. He analyzes observations and uses process models to interpret them. His recent study includes topographic effects on changes of AMOC and coastal sea level variability. In addition to research, he has taught 2 of the 4 core courses for the MIT Hui Joint Program in Frictional Oceanography, including large-scale ocean dynamics and small-scale ocean dynamics. Dr. Yang, thank you so much for joining us. At this time, I will turn over the controls to you.
Thank you. Can you see my screen? Okay, no.
We can't. Let's see. Okay, we can now. Go ahead.
Okay. Okay. So you can see my screen, right?
Yes, we can.
Okay. So thank you. So today I'm going to talk about the wind-driven variations of AMOC and the coastal sea level variations. So basically, the motivation is try to understand in the annual timescale variations that have been observed along the east coast of US by the tide gauge. So here I show 3 composite. Basically, I use a whole bunch of tidal stations along the east coast and group into the 3 regions. So the top panel shows south of Cape Hatteras, basically from Miami to Cape Hatteras. And the middle panel is mid-Atlantic coast. And the bottom panel is the New England coast. So the black line is monthly sea level anomaly, and the red line is 12 months rounding mean, and the blue line is the trend, is the cubic polynomial trend. And another set of observation is EMA observation. So one of the longest time series for EMA observation is made at the rapid array at 27° north. So what I'm showing you here is the monthly anomaly of the EMA transport, which is divided into a 3-layer. The upper layer, basically above the main thermocline, and the middle layer, which is the upper North Atlantic deep water, and the bottom layer would be the lower North Atlantic deep waters. And the trend, the linear trend, and the signal cycle are removed. So basically, what I'm been trying to do is trying to use a very simple model. It's a 3-layer model, so it's a simplest possible model, which I can think about it, and try to understand whether some of the observed variations of the EMA or sea level variability can be explained by a simple model. So basically, the underlying assumption is a large fraction of the variations that we observe are due to the barotropic mode or the fourth or second baroclinic mode. Okay, so here's my model. It's very simple. It's adiabatic model, 3-layer. All 3 layers are active. So the model domain extended from 30° south to 80° north, which is frame stretch. It's fully nonlinear, and each layer thickness is allowed to vanish. And the model is driven by ERA5 wind stress starting from 1979. And I use realistic bathymetries, and the minimum water depth is set at 5 meters. Okay. So I use the climatology wind and just drive it to the steady state. And here to show you the end of 100-year simulation. After that, I switch to interannually varying wind stress. Okay. So here's the comparison with the rapid observations. The black line is from observations. The signal cycle is removed. With the signal cycle, the agreement would be much better because signal cycle is so easy to simulate. So to assess whether the model can simulate in the annual variability or not. So I remove the signal cycle, and the red line is from the 3-layer model. So it's divided into 3 layers. The thick line is 3 months rounding mean. Okay, so you can see the agreement is quite well. It's not only capture large variations, like in 2010, there was a major reduction of EMA transport at the rapid line, but it also shows that the lower limb of the EMA variability is primarily confined in the bottom layer, so the lower Atlantic deep water layers, and the middle layer have relatively small interannual variations. Okay, this is from the model control run with the realistic bathymetries. There's another observation array with OSNAP, but OSNAP only have 5 or 6 years data so far. So it's very difficult to use such kind of short time series to compare the interannual variations. So what I'm comparing here is compare the 3-layer model with the EMA transport at the 4 latitude from the ECHO 4, which is a data assimilated product. So you can see that the model is not only doing a good job at the rapid line, it's basically is capable of simulating in the annual variations pretty much at all latitude. Okay, and it was found that topography is really play a major role in facilitating the ocean's response to atmosphere forcing. So what I'm showing you here is yearly anomaly from 2008 to 2010. Basically, I'm trying to show you the 2010, the major EMA reduction event. The top panel shows the satellite observed bottom pressure anomaly. The second panel show the ECHO 4, and the bottom panel show the model simulated. So you can see that the bottom pressure anomaly basically is a good indication of the geotrophic flows. Okay, so the pressure, the bottom pressure anomaly, the gradient of partial, the bottom pressure anomaly is proportional to the geotrophic velocity just on top of the seafloor. So what you can see here is you can trace the origin of 2010's MR reductions actually to higher latitude. And the wind-driven anomalies just propagate along F over H contour or the isoline of the potential vorticity. And there's some major intrusions along the mid-ocean ridge propagating southward, okay? And it's because the bathymetry, which shape the ocean's response, the pathway, that provide a very important connections between the subpolar basin forcing and the subtropical basin forcing. So now those are the EMA. So I'm going to talk a little bit later about the bathymetry effect, talk more about it. But now let's talk about sea level, okay? So again, here, the panel on the left-hand side is the monthly sea level anomalies along the East Coast, grouped into 3 regions. The model doesn't have the freshwater flux from the melt ice sheet, so we cannot simulate the trend. So what we did here is we remove the trend. So when we remove the trend, we see that the coastal sea level have a very robust interannual variations in all those 3 regions that's shown on the figures on the right-hand side, okay? And the pinkish line here shows the model simulations, the same 3-layer model, and compare with the sea level anomaly observed by the tide gauge along those 3 segments of the coast. The correlation coefficient generally is about 6.8 to 0.78. It's pretty good. I consider the signal cycle is already removed. With the signal cycles, the correlation would be much higher. And what you see is a lot of high frequency variability. So how about the interannual? So here's 12 months running means, okay, for the same comparisons with the tide gauge data, which is red, which is black, and the pink color indicate the model simulated sea level variations at the exactly same location of the tide gauge. You can see that south of Cape Hatteras, the model did a good job simulating a large increase that had been getting a lot of attention, basically from 2010 to 2016. There was a large sea level increase along this segment of the coast. And you can see the model actually simulated well of this, okay? Because the model is very simple and the dynamic is transparent, so we can actually separate into the open ocean forcing, local forcing, and the forcing in the upstream shelf regions. So here I'm showing you one example is that the remote forcing north of Cape Hatteras, but the forcing along the shelf actually make a considerable contributions to the sea level variations to the south of Cape Hatteras. And the connection is through topographic velocity wave. So basically, north of Cape Hatteras, the change of the wind stress over the shelf excited topographic velocity wave, and that propagating equatorward, and that affecting the sea level downstream. Okay. Then you ask that what will happen if the topography effect is removed? So here is the simulation. Basically, I use the identical model, but instead, the topography, I assume that the bathymetry would be uniform at the water depths at 5,000 meters everywhere. So what you can see that is that the variability much weaker, and the bottom intensified variation disappears. So basically, the middle layer and the bottom layer, the variability have about same magnitude. And if you look at the coastal sea level at the tide gauge stations, it's become very small, right? It's become very small. When you have those, when you remove those bathymetry effect. Okay, so I'm going to use the next couple minutes to talk about the predictions. So with those two-layer model, we try to experiment some sea level predictions. So basically, there's about 8 modeling center routinely put out 7 months prediction for the atmosphere. So there would be a prediction for the next 7 months for the wind stress. So what I'm using here is ECMWF 7 months predictions. So I did 4 years predictions and then compare with what actually observed. So model is forced by the predicted wind stress. So the result is kind of mixed. 2020 is kind of bad year, but the other 3 years, you can see the model does show pretty good prediction skills. Okay. Another one I want to show talking about is storm surge. That's one storm surge that get a lot of attention. It's a pre-Christmas storm surge last year. So what I'm showing you here is that high gauge at Sandy Hook, New Jersey. The upper panel showing the sea level high. A lot of them are due to the regular tidal cycles. So if you do the 24 months running mean, you can remove those tidal cycles. And if you compare with the model, which show the bottom panel, so the red line is from the tide gauge, the blue line is from the model. And for almost 9,000 hours, the correlation coefficient is 0.91. So the model does have a very good skill in simulating the storm surge. So the storm surge basically is a basin scale phenomena. So you do need a basin scale model. So basically here show you the development of a storm surge in those two storm surge in December. You can see the storm surge that is propagating from the open ocean onto the shelf and then propagating along the shelf. I'm going to jump into the summary here. So basically, seasonal and interannual variation of AMAC and coastal sea level are preliminary wind-driven, and the observed variations are resulting from the ocean's response to the atmosphere forcing, and the topography will really play a leading role in shaping such kind of response. And also coastal sea level variation is probably predictable. I mean, we need to study more about that. And also process model, which is very computational efficient and dynamic transparent, would be an ideal tool to explore such kind of predictabilities. Thank you.
All right, thank you so much, Dr. Yan, for that great presentation. We're gonna move now to our third presenter. He is Dr. Yan Xiao. He is a physical oceanographer in the Horn Point Laboratory at the University of Maryland Center for Environmental Science. His research centers on ocean's role in climate change, particularly multi-scale oceanic processes in the upper ocean and their regional impacts. Dr. Xiao, thank you so much for joining us. At this time, I will turn over the controls to you. Give me just 1 second. All right, now you're able to share.
Are you able to see my screen?
Oh, sorry, we
Hello?
can see your screen. Yeah, that was muted.
Okay, good. So good afternoon. So now my turn for I want to talk about the sea level variability in the Northwest Atlantic. So this part is also the part of the project we are working together. So just now, Ke and Jiayan already presented their part. So my focus here is mainly on the sea level changes on the multi-year and even decadal time scale. First, let's look at the tide gauge data from the several stations. So I pick up several tide gauge stations from the southeast coast, this black dot here, and also the northeast station around this dot. So for each station, I remove the reference level to get their yearly mean anomaly time series. So each color is for one station. You will see within each region, the tide gauge data is quite consistent with each other for the yearly mean. So then we can get the average, take that average as a representative time series for tide gauge anomaly data in the southeast and the northeast. So today I mainly focus on the period after 1990, when the altimetry data are available also. So overall, there's the sea level is rising in both southeast and northeast. That's a well-known phenomenon. Then I follow the method in the Decadal in 2023. This paper just came out a few weeks ago. So I follow their method to remove the vertical land motion, barostatic mass changes. This part is largely contributed by the the melt water from polar region, and also barometer contribution is largely from the sea level pressure in the atmosphere. So once remove this contribution, that mainly left over is the ocean dynamics, both dynamical and thermodynamical. So that original time series and the corrected data. So after remove this contribution, you see the long-term trend largely disappear, even though there's a kind of decadal change, but a lot of long-term trend is removed after this processing. So in recent years, a lot of people pay attention to there's the fast rising sea level rising in the southeast coast, and the Decadal's paper has a very nice summary. They use a singular spectral analysis to show the nonlinear trend for low frequency. So here is the result. So that horizontal axis is the time in different year. So that's a different tide gauge station. Starting point is the Gulf of Mexico, from west to east. From west toward east, here is the Florida, and then all the way north to North Cape Hatteras in North Carolina, and then further northward. So the color is their acceleration rate computed by their method. They find there after 2010, there's the large riding rate. They call it the acceleration in the past decade. This acceleration is a quite unique phenomenon over the past century. Here I think they are talking about this fast this acceleration mainly refers this period after 2010. There's a quickly increasing in the southeast, but north of Cape Hatteras in the northeast area, the decadal trend is quite weak. Here, when you look at the past decade, the trend is almost almost zero. So it's quite weak. They are consistent. So my data is consistent with theirs. Then and also Volkov also showed the acceleration in the tide gauge is part of the large scale basin-wide changes in the sea surface height. They compute the EUF mode in their altimetry sea surface height. This their special pattern. This is a temporal component in the blue line here. So the fast acceleration here, acceleration in the after 2010 also show their large scale pattern over here. And they attribute this pattern to the steric effect. So the similar spatial pattern, also the black, I think the black line here is a temporal component for the steric effect. So also has the acceleration in the after 2010 over here. And they also show that the color here is the percentage explained by steric effect. So along the southeast coast and also the Gulf Coast, the steric effect can explain more than 50, yes, many stations up to 70, 80% of the variance. They can, this variance, the amount of variance can be explained by the steric effect. Probably you will notice this large-scale mode has a very little projection to the mid-Atlantic region, middle Atlantic area. So their contribution percentage is less than 10%. So today I really try to show what happened in this region. So here is my data, tide gauge data, satellite altimetry data. The third one is the global ocean physics reanalysis data. We call it GLORIS. It's a global eddy resolving resolution, and it also has data simulation, temperature, salinity, also satellite altimetry. But the tide gauge data is not assimilated. So I use the tidal gauge data as an independent validation to compare the tidal gauge sea level and the glorious data. This is the correlation coefficient for different tidal stations. Using monthly data, using yearly mean. So over the majority of the station, the correlation is quite high, more than 0.7. The red text here is not significant over the 95 confidence level. So the most station is significant. So that means the glorious capture the right phase in sea level change. How about their amplitude? So I use the ratio for the variance in glory over the variance in tidal gauge. This is their ratio. Again, monthly data, yearly mean data. Over the southeast area, the ratio quite close to 1.9. So that means their amplitude is almost the same. For the northeast area, the glories seem to underrepresent the tidal gauge data. For the yearly mean data is only capture about half. So now let's zoom into this area, see what happened. So you can show the sea level anomaly in the glory data within this box. This box we call is mainly located in the mid-Atlantic bight. This black box here. So all the grid point within this box, I sort this grid point into according to their water depth. So the black line here, the top panel, is the tidal gauge data. So that coast sea level from tidal gauge. So the red line here is all the grid point less than 30 meters. We can define this as the inner shelf. But I also tried 20 meter, 40 meter, and the similar result. So yeah, within this area, that's about 300 grid point. So magenta is the middle shelf and outer shelf. So this black line here is 200 meter depth. So middle shelf and outer shelf. And the blue line here and this line here, sea level anomaly. So that's a deeper part, larger than 2,000 meters. So when you look at the tidal gauge data, sea level, and the inner shelf, red, and the magenta, middle, and outer shelf, the sea level in these three parts is quite similar. But when you compare the tidal gauge with the deep ocean changes, they are not correlated to each other. Some period is anti-correlated, some part is positive. So overall, the correlation is very low. So that result tell me, the tidal gauge data on this interannual changes is similar. Tidal gauge data is similar to the sea level changes over the continental shelf, less than 200 meter depth. Next, let's look at the east part. For the inner shelf, the red, again, the original sea level, no trend removed. The bottom is detrended. The blue line here is the steric effect. The steric effect is mainly using the temperature salinity in the local, so every grid point. So that means the inner shelf. So the local steric effect not able to explain the sea level changes in the inner shelf. But when you look at the middle and outer shelf, between 70 meter to 200 meter, again, the magenta line is the original sea level. Blue, again, the steric effect, local steric in the middle and the outer shelf. So in the original sea level, there seems a long-term trend, but this trend doesn't show up in the steric effect. So that means the steric effect is not the main contributor to the long-term change in sea level. It's very likely due to vertical land motion and also by static mass changes. But when the long-term trend is removed, the interannual changes here, the steric effect seems to very closely follow the sea level changes. Especially after 2010, the steric effect, blue line here, caused a decrease sea level. That's a big contrast to the southeast area. Near the Florida, the sea level is rising in this period. But here in the mid-Atlantic region, the steric effect causing the decrease from 2010 to 2015. Then again, I show that panel again, so sea level and the steric. Separate the steric effect, the blue line here, to two factors. Salinity, the green line here is a healing component, and the green line here is the temperature, thermal. So the both components have some degree, compensation, but overall the total stereo effect somehow follow the salinity component, the healing component. In the 2015, from 2010 2015, salinity component, the healing component, caused the sea level reduction in 2015. So back to 1998, salinity even caused the sea level rise. Now let's show the what happened in these two periods. So 1998 and the 2015. Salinity anomaly at 30 meter depth, and the temperature anomaly for both years. So in 2015, saltier, warmer, and in the 1998, fresher, colder. So there's a competition between each other, but the salinity has a much larger, amplitude. So salinity is the main dominator for the stereo effect here. So I want to use the last few minutes to show the possible mechanism, what drives the salinity changes over here. Actually, the Grosky in 2017, they have also found the salinity increase in the 2015. They're using the satellite data in the sea surface salinity in two satellites, Aquarius and Smooth. This anomaly. They find the 2015, the salinity positive anomaly, so the salinity increase. This from 2011 all the way to 2015. They also find the salinity increase. And they also compute the EOF, sea surface salinity and temperature, sea surface height. This is their special pattern in color, and their temporal component. So that they are using different data set. So let's look at the EN4, one that's from the UK data set. So their temporal component here, the dashed line here, EN4. So in the 1998, they're negative temporal component, so it's a fresher in this region, and the 2015 positive, so it's a saltier. That's a similar signal to what I showed just now. And the black vector here is the wind pattern corresponding to this pattern. They find that there is this pattern is associated with the southeasterly wind. They argue that the southeasterly wind can modify the current in this region. So near this region, near the shell break, there's the shell break jet. They have different name. Like in this region, they call it the Scotia shelf current over here. So this time mean current in sea surface, this current can bring the fresher, colder water from higher latitude. So this wind pattern can reduce this current. So the lower panel shows the anomalous current associated with this pattern. So it's northward anomaly. So that means this southward mean current is weakening. So the current is weakening, the less fresher and colder water transport to the lower latitude. That's why it has a salinity increase and temperature increase. And then on the other hand, and the Goncalves NATO also find the Gulf Stream pathway also shifting towards the nearshore region. So the upper left shows the mean dynamical height and mean dynamic topography, the long-term mean. So the Gulf Stream path is roughly this area. And they also show the sea surface height in this, the region enclosed by the black line here. So the bottom shows the sea surface height. They find around 2010, there's a suddenly increase of sea surface height. So that means the Gulf Stream path, they attribute this increase to the onshore shifting of the Gulf Stream path and to bring the more higher sea surface height to this region. Associated with the onshore movement of Gulf Stream, more warmer, saltier water bring toward the slope region, continental shelf break. And this current, this anomalous warmer, salty water is a favorable condition for the downstream to increase the salinity and the temperature. So that's the two possible, dynamics for the increase in salinity and temperature. I think I almost run out of time. So some take-home message. First one, sea level along the northeast coast and also the continental shelf region are similar. They don't show the fast rising after 2010. And the steric changes are dominated the sea level interannual changes in this region. And salinity is a big contributor to determine the steric effect. And the salt advection due to the anomalous current working on the mean salinity gradient is the primary driver to cause the salinity changes in this region. I think I'll stop here. Thank you so much.
All right, thank you so much, Dr. Xiao, for that great presentation. And now, as I said in the beginning, I'm going to open up the floor for questions from the audience. Remember, you can use the raise your hand feature or type your questions in the questions box. And it's open for questions for all our three presenters. I don't see any so far, so I'm going to go ahead and ask one myself. Is there any future work that you're going to work on the next months, years on this topic? And this is for all three, since I know you work together.
Yeah, I can talk about a little bit. So we are going to continue to explore the predictabilities about the coastal sea level. There's a different modeling center. We only use ECMWF, and we'll try to see other product just to explore the coastal sea level predictability. Another topic is the storm surge. That there have been a lot of talk about climate change might result in the change of the storm, both intensity, location, frequency, and we can use the model to assess that the impact of such kind of change of storminess on the coastal area. I mean, you can imagine that if a storm, the location had been like a jet stream move, and the storm's location had been moved because its pathway is affected by topography. So, so how would that affect the storm surge? So, yeah, that is something that we've been one of the topic that we are working on right now.
Okay.
Maybe I can just add a few sentences as well. So the other topic we are interested in pursuing is the co-occurrence of extreme events. For example, storm surge and also heat waves, those type of because there's a possibility they can be driven by the same process. For example, very strong wind events that can, like I showed, bottom intrusion, but also that can have a big impact on the coastal sea level as well. So the co-occurrence is something, very interesting in pursuing as well.
Okay. There's one question, and it's probably for two questions. So the first one is for Dr. Chen. If the time mean Gulf Stream position shifts northward, do we still need preconditioning by cyclonic eddies in order to warm the shelf?
That's a good question. My gut feeling is if we have more persistent presence or of warm and salty water at the outer shelf all the time, then I tend to think that we do not necessarily need the preconditioning step. Rather, if the wind is relatively persistent over a certain period of time, that itself should be sufficient in driving those extreme events. In other words, if we were to look into the future, if we think of the expansion of subtropical gyre, for example, or the northward shift of the Gulf Stream, I tend to expect higher frequency of those type of events.
Okay. And as a follow-up, does the frequency of cyclonic eddies encountering the shelf break change?
That I cannot answer because one thing, like I mentioned, is the lack of a sufficient high resolution observations is prohibiting us from characterizing the temporal variability of those eddies. You know, synoptic ship surveys in the past have captured them, you know, a few times, but we do not have a long-term like time series type of data to really say something about their frequency. But that's an excellent point. Maybe, you know, with more observations coming, we're hopeful that we can answer that.
All right. The second question, have you seen any difference in lead times for skillful prediction based on region? Can Southeast be predicted more months out than Mid-Atlantic?
So far, we have only explored one. We just started quite recently about the predictions. So we haven't really looked beyond Woods Hole yet. So we just look at try to predict Woods Hole, and our plan is to expand it to other region. One thing I would like to comment on is we did compare the model simulation along the East Coast and the West Coast, and the model skill along for sea level variability along the West Coast is much higher than the East Coast actually. But this talk is about the Atlantic, so I did not touch on that. So yeah, so I don't see why. I mean, the South Atlantic coast will be different from Woods Hole, but we haven't tried that yet.
All right. And the last question is for Dr. Shan. What boundary conditions are used for ROM simulations?
Oh, in this particular experiment, I used the global data assimilative HICOM. So HICOM encoder, global ocean forecast system 3.0, I think. But it's not, you know, before fitting global model into the regional domain, some necessary, you know, by correction procedure has to be done. So, but it's largely based on the global HICOM, data assimilative HICOM.
All right, and with that, we would like to thank everybody for joining us for this set of presentations in our series of the Decadal Climate Variability and Predictability Studies. I would like to thank today's presenters, Dr. Cheng, Dr. Yan, and Dr. Xiao for taking the time to share their work. The recording of today's webinar will be available within the next week on our website, cpo.noaa.gov/cvp. You'll find the past sessions there as well. We hope that you enjoyed not only today's webinar, but all the sessions. It's been 8 great sessions with great science, great research, and obviously me and CVP's program manager, Dr. Regina Sells, can't wait to see what's out there in the world of science, specifically in this topic. So stay tuned. As you can see in your screen, that's our website, that's the CVP program staff, and please stay tuned for future CVP webinars. We like to do webinars to see, you know, the science that's out there. So thank you again, and we'll see you very soon.
Thank you.
Thank you, Jose.